Could someone that is online confirm that they can hear me?
No.
Oh, thank you, Vanessa.
Fernanda, can you try again to say something, please?
Sure. Can you hear me now? Hi, hello.
Yeah, ahí estamos. Yeah, now it's working.
Oh, great.
Okay, I will first introduce you to the audience in Spanish, and then I will give you the microphone to speak. Disculpas por estos minutos de atraso, tuvimos problemas técnicos, pero ya estamos con nuestra siguiente presentadora en línea. La siguiente contribución tiene como título Variable Selection in High Dimensional Linear Mixed Effects Models y está a cargo de la doctora Fernanda Lang Schumacher. Ella es doctora y máster en estadística por la Universidad Estatal de Campinas y licenciada en estadística por la Universidad Estatal de Maringá en Brasil. Se desempeña como profesora en la Universidad de Ohio State, trabaja con modelos de regresión mixtos y en los contextos de series temporales y datos longitudinales, principalmente desde un punto de vista frecuentista. La mayor parte de su trabajo está disponible como paquetes de R de código abierto, lo que facilita el uso de modelos flexibles en aplicaciones. El principal de investigación de la doctora Schumacher ha sido el desarrollo de modelos estadísticos sólidos que puedan adaptarse a características específicas que se encuentran con frecuencia en las aplicaciones, como valores atípicos, asimetría, dependencia del tiempo y censura. Vamos a comenzar entonces. Fernanda, the floor is yours. You have 15 minutes for your presentation, and thank you very much for your time and waiting time.
Of course. Good morning, everyone. It's a pleasure to be here with you today, and thank you for the very nice introduction. Well, I do apologize for not being there in person. I wanted to go, but I couldn't at this time of the year, unfortunately. But I'll do that next time for sure. And also, I do apologize for not speaking Spanish. I am from Brazil, as you could guess by the universities I studied in. And my primary language is Portuguese, and I can understand Spanish well, but apparently Spanish speakers can't understand my Spanish, so English was safer. But feel free to ask questions in Spanish. I can usually understand them, and I'll let you know if I can't. So I'm gonna talk about variable selection in linear mixed models, and this work is in collaboration with Daniela Oliveira and Victor Lachos. Daniela is also from Brazil, and Victor is from Peru, but is working at UConn in the US now. Well, first, I'm not sure if everyone is familiar with mixed models and longitudinal data or repeated measurements data in general. So I want to get started by a 1-minute introduction to mixed models. And basically, in the context of longitudinal data, what we usually have is something like this plot here. When we follow a few subjects or sampling units over time. So we have repeated measures for different times in the same subject. However, we're still interested in estimate the populational effect. So the general average over all subjects effect that is represented in this plot by this black line here. But we need to account for the dependence, the dependence that comes from this repeated measurement. So in mixed models is a tool that we can use to handle this. It's not only useful for longitudinal data, we could have any kind of clusters. We can think about students within a classroom, or anything that is like nested, or that we can see like a natural cluster. Any kind of repeated measurement would work. We can use some model like that. And it is also particularly useful for missing data, which is also quite common, that we don't have the exact same number of observations for each subject or for each sampling unit. What these models do, why they're called mixed, because they have both fixed and random effects, and the fixed effects will be the parameters associated with the entire population. So this is the parameters that the whole population share. And the random effects will be an additional source of random variability that comes in the individual level, that comes from sampling these individuals at random from a population. So this is the way we can represent this as the model as an equation. So the traditional regression model would have something like this, like y equals to x beta, and in here we are adding an additional source of variability. So we are adding the b that are the random effects. And z here represents the design matrix corresponding to the random effects vector. But we also have the X matrix, that is the design matrix corresponding to the fixed effects. Now, as I mentioned, we have two sources of variability. We still have the random error at an observational level, but we have an additional source of variability that comes in the individual level. So we have two sources of variabilities. And this adds a lot of flexibility because we can accommodate this dependence that comes from the repeated measurements. But it also, as always, when we add flexibility, we need more assumptions. There is a trade-off there. And there's also is something else to consider. We could have, in this context, we could think of selection of variables in two settings. One would be in X and the other one would be in Z. So we can select both the variables from the design matrix of the fixed effects and from the matrix associated with the random effects. But in this work, we are focusing on the selection of variables in the fixed effects part. So we are just interested in selecting the variables that all the population share. And this work proposes to use the expectation maximization algorithm to solve problems of penalized maximum likelihood estimation. And we proposed an algorithm that is called YAM-LM-LASSO. And it combines the optimal, efficient estimation from GLMNet package that is designed to handle independent data. So it combines that with the mixing variable repeated measurement setting from mixed models. And it can be used in both settings with less variables than number of observations, but also in the setting with more variables than number of observations. And I will show you some results of how this worked, and it presented interesting, consistent results for the cases we considered. So how do we select variables? Similar to what we would see in a regression setting, what we do is adding a penalty term as a function of beta that is regulated by this parameter lambda. So we add this term, this penalty, to the log likelihood function, and this will also yield penalizing the complete data log likelihood function that we have in the EM algorithm. So we can write the complete penalized log likelihood function as this. This would be the kernel, the traditional log likelihood function from the mixed model I presented to you before by assuming normality. So this would be the part from the individual level, and this other part would be from the random effects. And we can, so what we propose is to penalize this function in order to enforce variable selection along with estimating the parameters. And I will show you briefly what the algorithm looks like. We first need to choose to fix for a fixed value of lambda of that regularization parameter. For a fixed value of lambda, we initialize it beta, sigma, and d. So sigma is the variance associated with the random error, and d is the matrix associated with the random effects. So we have more than one source of variability, we have more than one variance to estimate, and that's what's written here. So we initialize them like this, and this is just a L1 penalty for beta, because we are using a lasso penalty, but this could be any different penalty. It would work the same way. And then we specified at each step, we have a E and a M step, which is traditional from the EM algorithm. And in the E step, we compute these expectations that will have these expressions, where we transform, let's say it like that, the response variable by removing the effect of the random effect at each iteration. And we also use this transformation of lambda that have this this expression. And then in the M step, I'm sorry, someone mic is open. In the M step, we optimize, we compute the we maximize that complete data expression. I'm sorry, Michael, could you turn off your mic, please? Thank you. So in the maximization step, we compute this, we optimize that expression as a function of the parameters, and we'll have something like this, where for sigma and for the